recorded. Okay. Yeah, thank you everyone for showing up. And I got to know that there's a football game going on right now as well. And still, you guys are here to listen to my research. So even a bigger thanks for that. Okay. I'm Unnat. I'm a PhD student at University of Illinois at Urbana-Champaign. And today I'll discuss some recent progress we have made on collaborative embodied agents. That is, AI agents that can collaborate in virtual visual worlds. Let me set the pointer. So yeah, let me set the groundwork for the research I discussed today first. So we humans collaborate and communicate with others in our environment. We coordinate our actions during driving. We strategize while playing football and while scoring goals. And we effectively communicate to move furniture with our friends, or at least we try to do so. Now, robotic agents are being built to closely emulate human behavior, including this collaborative aspect of our intelligence. As expected, working with hardware requires focus on low-level control. However, these high-level behaviors that robotic agents should know get missed out. Particularly learning and interpreting collaboration and communicative behaviors is difficult on real robots. Other skills such as long horizon planning and completing increasing complexity of tasks are difficult to study in the presence of low-level control. Hence, a good trade-off to strike is to work within high-fidelity simulated environments. The built-in physics in these environments allows agents to interact with the environment objects. Now, within these embodied virtual environments, low-level control can be abstracted away so that the focus can be on other aspects of learning. Now, within these virtual embodied environments, the community has developed agents to solve realistic tasks, such as visually navigating to a given goal. Here, an agent is navigating to a room in the house. Or doing instruction following, where an agent navigates following a natural language instruction given to it. Or embodied question answering, where the agent needs to explore the environment to be able to answer a question. For example, the question here is, what color is the TV stand? The agent roams around, finds that the answer is dark blue. Now, my interest and research focus has been on collaborative embodied agents. That is, agents that can collaborate to solve tasks that no agent alone can solve. And to build such collaborative agents, the agents must have the skills to navigate using visual inputs, communicate. They should be able to communicate their intentions and coordinate their actions. Now, visual navigation in near photorealistic scenes has an extensive history. However, they study only single agent settings. Similarly, work on communication has produced agents capable of complex dialogue, but on static data sets or simplistic environments. And finally, studies of multi-agent coordination have largely ignored the complexities of ecocentric vision and focused on these particle worlds. Hence, a principled study of collaborative embodied agents is necessary to scale vision research beyond single agent applications. And that brings me to the meat of this talk. I've structured this talk in 3 parts based on closely connected works. In part 1, I will introduce the first collaborative embodied task, which we called Fern lift. We'll interpret the communication that emerges when agents solve this task. We'll also see the effects of explicit and implicit forms of communication on the performance of these agents. In the second part, I'll increase the complexity of the task to include the moving of the lifted furniture. Then I'll show you why existing multi-agent policies struggle at such a tightly coordinated task and how we can fix it. In the third part, I'll introduce a collaborative teacher-student learning setup where the two agents live in different abstractions of the same world. This helps us to train agents with minimal supervision of terminal rewards. Okay, that's the talk at a glance. And let me dive straight into part one. Now, to study collaboration between agents, we introduced the Fern lift task. The Fern lift task can be broken into two stages. First, the agents must visually navigate to a target object. In this case, the agents navigate to a TV. And after finding the TV, the two agents must coordinate to lift it at the same time step. Note that the lift or pickup action will fail if only one agent executes it. Thus, an optimal action from the perspective of a single agent is suboptimal. The Fern lift task stands out in previous embodied tasks for two important reasons. First, the interaction and coordination to lift furniture makes this task harder than prior navigational tasks in static meshes. Second, the presence of multiple agents makes the environment non-stationary and introduces challenges of credit assignment, making it even more challenging than navigational ones. But what do these agents see when they're trying to solve furniture lifting? The agents operate on their ecocentric observations. The ecocentric observations of the two agents are shown on the left. For simplicity, each agent sees the other as a science cylinder. In later versions, we were able to get robot avatars to replace these cylinders, so you might see a mix of both in the results. Now, the top-down view that I show on the right is not available to these agents, but will be used for interpretable visualization. Now, given the Fern lift task definition and these egocentric views, how to design models to solve such collaborative tasks. Here, you might be lured to think that, hey, why don't we just pool the observations or information of all the agents? We can pass this through convolutional and recurrent blocks. And this central agent would compute a joint distribution over the product space of each of the agents. So while this central agent is rich in representation, it simply doesn't scale with the number of agents because both the model complexity and the policy parameters blow up exponentially as we increase the number of agents. Moreover, a centralized architecture relies too heavily on perfect communication. Transmitting entire local observations to a central server needs high bandwidth. Similarly, the communication from the central server to the worker agents would include what actions to take. This remote processing is just too brittle to losses in communication. So all in all, in summary, the community and we have focused on building multi-agent policies that can be decentrally executed. So here is a decentralized baseline model for furniture lifting. Now, CNN processes local visual observations. The history of previous observations is captured in, for example, a hidden LSTM state. And using this current observation and this history, the model generates a local belief for each agent. This local belief is the agent's understanding of the world and can be used to estimate the state's value and actor policy. Now let's see a trajectory of this baseline model on this Fern lift task. I reemphasize that the agents only see their respective first-person ecocentric views. This top-down view is for illustration purposes only. Note that these white triangles denote the viewing direction. The TV here is marked in yellow, and this thick white strip is actually a wall which has a door in the middle. Now, the red and the green agents must find the television and coordinate a team lift. The red agent is initialized close to the TV and quickly finds it. The green agent begins on the wrong side and has to backtrack several times before finding the television on the other side of the wall. Here it crosses the door and finds the TV. Now, to improve performance, the agents must learn how to communicate. Just like I would shout out to a friend that, hey, come over here, I can see the TV on this side. Or coordinate the pickup using strategies like ready, steady, go. So let's try and incorporate this communication between agents in our network. So in our decentralized baseline network that I showed before, we incorporate communication between them, between these agents, using novel communication modules. These modules help the agents to send a message from a fixed vocabulary to another agent, to the other agent. These modules also help refine the local belief of the agent. Now let me unpack the first stage or the talk stage of communication. Notice there are these two stages of talk and reply. Let me unpack the first talk stage of communication. So overall, the objective of these communication modules is to create a message signal for the other agent, which is msend, and generate a refined belief, which is h hat. To do this, it utilizes the current belief h tilde and a similar message from the other agent, which is m received. The superscript of t here simply denotes that these variables are of the talk stage. Now to generate the first output, msend, we linearly combine two talk symbols, T1 and T2, by generating appropriate weights PT1 and PT2. We also experimented with more talk symbols, but for the purpose of simplicity and interpretation, I'm showing two talk symbols. Okay, now with this combination, the agent can create the msend, which is the message sent to the other agent. The module also receives a similar message from the other agent. This is m received. This received message helps generate the second output of the module, which is the refined belief. More specifically, the received message, m received, is concatenated with the current belief h tilde and transformed to create the refined belief h hat. This completes the talk stage of communication, and the reply stage is identical in structure. Just like talk symbols T1 and T2, there are reply symbols R1 and R2. These reply symbols are combined using inferred weights PR1 and PR2 to create the message msend superscript R. Hence, each agent learns to create a talk message by combining two talk symbols and creates a reply message by combining two reply symbols. And the final belief H is utilized for actor critique or imitation learning based training. We refer to this message-based communication as explicit communication between agents. Now, let's see how these agents perform with this explicit communication baked in to the network. With the described communication modules, the agents can complete the task almost twice as fast as agents without explicit communication. Also, the number of instances where only one agent attempted pickup, that is unsuccessful pickups, is reduced from 6 to 0. So symbol-based communication or explicit communication is indeed useful for the agents to collaborate. But what do these agents talk about? So we've qualitatively and statistically interpreted this communication learned by the agents. To put it in simple layman terms, we found that in the talk stage, the agents give cues of when they are near the TV. Hey, I'm near the TV. And in the reply stage, they communicate their intention to pick up the TV so as to coordinate their pickup actions. I'll give you a sneak peek into the statistical analysis we did in our paper, but I'll defer all the details for further reading. So for this, I will plot probabilities inside these communication blocks. So here I have plotted the probabilities PT1 for both the green and the red agents. And what we found is that there's a strong correlation between when the agents see the TV and the probability that is inferred here, which loosely which we found to be statistically significantly related to this notion of, hey, I am near the TV. Similarly, in the reply stage, we found strong correlations of a dip in probabilities associated with a pickup action. So agents indicate to the other agent that I'm about to do a pickup so that they can coordinate their pickup actions. So we found, again, a statistically significant correlation between this event of dips in probabilities and their pickup actions being coordinated. So this summarizes the interpretation of the explicit forms of communication between the agents, and brings me to an interesting aspect, which we call implicit communication. Rather, I'll call it like implicit cues that people use for communication. So this is a slightly nuanced version of communication. Now, by being able to see each other, the agents get information about the location of the other agent. Hence, the visibility of the other agent serves as a form of implicit communication or an implicit cue about the other agent, right? Now, we experimented by making these agents invisible to each other. So we let them be visible to us so that we can interpret and understand where they are. By taking away this implicit in addition to explicit communication, the agents become incapable of solving this episode that I showed before. And we quantify these effects of communication in these results. The x-axis will show the number of training episodes. On the left, we plot the percentage of successful episodes, higher the better. In the middle, we plot the number of unsuccessful pickups per episode. This is lower the better. And on the right, we plot missed pickups, that are opportunities where a pickup or a joint pickup was possible, but the agents didn't pick the furniture item. Again, lower the better. Now, the red plot is without implicit or explicit communication, and it performs the worst. The orange and the green correspond to only implicit communication and only explicit communication. And both communication methodologies help individually, and when combined, perform the best. This brings me to the end of the first part of our discussion, where the takeaways are that we study collaborative behavior in visual high fidelity environments. We find that explicit and implicit forms of communication are helpful. And we notice an emergence of interpretable communication pattern when the agents learn to communicate with each other. I'll pause here for some questions. If people have any questions, I can answer them here now and then move on to the second part.
Maybe a quick question on the your action space, if I may. So the trajectories, they looked rather rectangular or like on a grid to me. So what is the action space here? What can the agent actually do? Move left, right, up, down in the grid world?
So as I mentioned, maybe let me scroll to this slide. As I mentioned, these agents are not operating in these grid worlds or like the top-down worlds. They're operating in their egocentric images. So let me just clarify that first. And you're right that as you notice, these trajectories in, for example, this episode, they look rectangular because the action space is curtailed to be a 90-degree rotation. So instead of up-down, these are egocentric action space. So there's move ahead, turn left, turn right, and there's this pickup action as well.
Okay.
In later works, we've been able to also, like, these environments became amenable for continuous control. So you could do finer rotations, you could do partial movements as well, so that if you hit something, you get stopped at where you hit the ball.
But so is there any continuous visual stream there, or is it basically discretized that if the agent faces one way and then does a 90-degree turn, it immediately gets the next image, which is turned by 90 degrees and nothing in between? Or is there anything in between?
That's a great question. I have the manifestation, or like the implementation that we have here, it sees the next image directly. So it doesn't see anything in between. And you're correct in noticing that it has useful information in that transition as well, because of the field of view being limited. If it saw the continuous transfer, it would be able to see more information. But this has been formulated as a standard MDP problem, where you take an action and then you get a new observation. And this new observation is the rotated 90-degree rotated frame that you see.
Okay, thank you.
Great questions. Good to see that you got into the details of things and understood them well.
May I ask a question about the communication?
Yes, please go ahead.
Yeah, so in the communication phase, you mentioned that there are two kinds of vocabulary. One is I'm near the TV, one is let us pick up. So is it predefined or is it learned?
This is learned. So this is why I keep emphasizing that this is emergence of communication. We put in the basic structure for communication, but how these agents, what meaning they associate to these symbols and how they use it is totally up to the agents. And they talk in this language space, which is these probabilities going up and down. And we do the demystifying part of correlating it to things which we understand as humans. So they talk in these probability symbols, which is gibberish if you don't have a lens to interpret it. And that's why we put in this lens of statistical correlation studies. And the inferences we found in layman terms were that I am near the TV and hey, let's do a pickup.
Would they shout out that they're near the TV even if they saw the other agent being close to the TV as well? Or is this used in the absence of, I think you call it explicit information about the other agent's position?
Right. Implicit information about the other agent.
Sorry, right? Implicit. Yes, sorry.
Yeah, right. That's a good point. So what we did is we found a stream of relevant events, like visibility of the TV to a given agent, and did correlation studies between the talk symbols and the reply symbols with those events. The event that you're proposing is a conjugate one, that visibility of the TV, but without the other agent in view. Yep. We didn't do, I think that's a good point, but we didn't do a statistical analysis with that variable per se. But we did it with these marginal variables, that is, can I see the TV? And can red agent see the TV and the probabilities of the red agent? And can green agent see the TV and the probabilities of the green agent? And we found strong correlation there. But that's a good point, that maybe the correlation is even more pronounced when the other agent is not in view. Because that's the time where you want to indicate really to the other agent that come over to this side, or I am close to the TV. That's a good point. Yeah. Okay. Any more questions? Otherwise, I'll move on to this second part of the talk, where I'll introduce this intricately coordinated task. And having covered this communication aspect in details in the first part of the talk, I'll focus on the actor head. That is, how can we design better multi-agent policies for these agents? Okay. To advance the research on collaborative agents, we plan to test them on a harder task than furniture lifting. And we analyzed this task and found two places, or two things which we could do. We found that the furniture lifting requires only one step of coordination. That is this lifting action at the very end of the episode. Till then, all of it can be done independently with the other agent if they wanted to. So we wanted to formulate a task which requires coordination at every step of the episode. And that brings us to the furniture moving task. This is a natural continuation of the Fern lift task. Here in Fern move, agents relocate a heavy furniture item to a desired goal. In this particular example, the blue and the red agents are tasked to move this heavy furniture item, television in this case as well, to the goal, which is a yellow table. Now, agents are initialized holding the object in randomly chosen locations. There are obvious constraints imposed on the agents. Particularly, the agents must remain close to the television, emulating the behavior of holding the TV. Also, the agents must coordinate their actions to move the TV. For example, here, if the blue agent chooses to move with the TV backwards, then the red agent must choose to move with the TV forward. Hence, agents must communicate and coordinate at every step of the episode. During the course of the episode, the agents must learn to plan paths, avoid obstacles, and deal with partial and mutual occlusion. So, for example, here, note that the blue agent can only see the goal, making communication even more important in the presence of this mutual occlusion. And finally, when the agents bring the heavy object to the goal, they can successfully complete the episode. Now, when we deployed the two-body network architecture and that I discussed in the first part of the talk on this intricately coordinated task, it failed to coordinate actions. We dug deeper to understand the underlying issue. The two-body network, or more generally, any decentralized architecture for multi-agent tasks, captures a single or marginal policy per agent. Let me explain this with particular variables. So if the agent one's policy is pi1 and agent 2's policy is pi2, and since these agents are sampling independently from these distributions, the joint distribution that these agents can capture will simply be the outer product of pi1 and pi2. Generalizing this to n agents, we would have an outer product of n marginals. Evidently, this outer product is severely restrictive in representing a desired joint distribution. Now, central models could come to our safe here because they can capture joint distributions directly. But we are aware of its pitfalls. And as I mentioned before, they do not scale and they have communication issues. So we cannot deploy, or we do not want to deploy a central agent. Hence, we need a bridge between the decentralized execution here and the central methods here. Let me give you an example of this phenomena of outer product and its limited nature. So suppose this is an optimal joint that you're trying to capture. I've just put in a 4x4 matrix, which could mean actions of agent 1 on the rows and actions of agent 2 on the columns. Now, this is the optimal joint you wanted to capture. And what do marginal agents capture? If you marginalize this joint, these are the marginal policies of the agents, simply summing along rows and summing along columns. And the effective outer product or effective joint that they capture is this. Notice there's a lot of error in estimation because this outer product by definition has to be rank 1. This is the problem with marginal agents. And we want to deploy this idea of which we call mixture of marginals. What is mixture of marginals? We will put in multiple policies for each agent. So for example, here both of the agents have 4 policies. And then we will interleave these marginal policies using a mixture weight alpha to get this outer product, to get this joint distribution, which is a summation of multiple outer products. Since it is a summation of multiple outer products, it can, by definition, be higher rank than simply rank 1. So this is the key idea behind our approach, which we call mixture of marginals. Now it's just about implementing mixture of marginals using deep nets. So instead of a single marginal head like we had in the previous part of the talk, we will compute mixture weights alpha and k policy components per agent. That's step one. Next, we will sample the value I from the categorical variable alpha to obtain which of the policy components do I want to activate. This sampling can be done using a shared seed so that each of the agents shares the same value of I. And finally, we can independently sample each agent's action from its ith component. So with this, we can implement the key idea of mixture of marginals, which can capture much higher ranked joint distributions than a single marginal per agent. Now I'll get into some details which will be useful to interpret the policies that these agents learn. As obvious, we should talk about the action space of these agents. So let's see the action space per agent. So the agent, any given agent can has its own single agent navigational actions like move ahead, rotate left, rotate right, hold on to the TV. Oh, this hold on to the TV is like a pass action. It also has these move with object actions where the agents can move with the object along with, can move the object along with themselves as one assembly. Now the agent can move with the object in any of the 4 relative directions: forward, back, left, right. The agents can decide to rotate the object at its current location in a particular direction. And finally, the agents can choose to move just the TV and not themselves. So the agents can move the object in any of the 4 relative directions again. All in all, there are these 13 actions. Now let's see how these per agent actions couple with each other. I've put in the action labels for both of these agents. Now, a single agent can't move freely like just without the other holding on to the TV. So this leads to these valid actions. So one of the agents needs to hold the TV if the other is moving, and this needs to hold the TV if the other is moving. Note this inverted L shaped. Next, if both agents decide to rotate the TV, they can surely do that. What about the move with object actions? Here things get a little interesting. The coordination of actions would depend on how agents are oriented relative to each other. For example, if both the agents are facing the same direction, they could just decide to move with the object in any of the 4 directions. Both of them decide to move forward, they can move forward. If both of them decide to move left, they can move left. Hence, this diagonal pattern emergence. Similar story for actions where only the object is moved. Both agents need to coordinate to move the TV in any of the 4 relative directions. It is easy to verify that such a matrix is in fact high rank if one associates non-zero entries for each of these valid actions. It would actually have at least a rank of 10. Notice that only a tiny percentage of the actions are valid at any time step, making rewards very sparse. Now, what if the blue agent was oriented 90 degrees to the right of the red one? A similar coordination of the joint action space would exist then. So if the red agent decides to take the object forward, then the blue agent needs to move to its left. This guy goes forward, this guy needs to move left. Or more generally, this is the overall coordination of the joint action space of the 2 agents for furniture moving. Contrast this to the coordination of furniture lifting, where 64% of the actions are valid at any time step, and the optimal policy is low rank. Empirical runs can validate these mathematical intuitions. Let's see the difference of success rate between the central and marginal agents. In the Fern lift task, the gap between the central and the marginal agents is just 0.6% in success. Other metrics like failed pickups show that central agent is better, but not by much. In contrast, in the Fern move task, this gap is drastic, a whopping 32%. This qualitatively establishes how tightly coordinated this furniture moving task is. Next, we discuss a way to visualize and interpret these policies. So we plot an average of all actions attempted by the agent over the test set. We obtain a matrix which looks like this for the central model. Notice the inverted L-shaped of the single agent navigational actions and the block diagonal nature very adherent to our expectations for the central model. Now compare this to the marginal model. The matrix is banded in which is a characteristic nature of rank 1 distributions and has a lot of probability mass dispersed over invalid actions. This is reflected in metrics where the central agent is much more successful than the marginal, where the marginal agent actually ends up failing its actions even as high as 65% of the times. The mixture model or the sync policies bridges the gap between these central and marginal models with a success rate of 59% and a lower percentage of uncoordinated actions. Let's see these agents in action in qualitative runs. For these qualitative runs, let me just recap what we plot in these top-down maps. The furniture to be moved is a TV, and the goal object is this yellow dresser or yellow table. And as the agent, as before, these agents are marked as these colored disks, and the triangles connected to these circles denote the orientation of these agents and the approximate field of view. Also notice the colors left behind by the agent as they move. Agent 1's trajectory is red, agent 2's is green, and the TV's is blue. Okay, I have added the egocentric views beside the top-down view for you to see what the agents actually see, but focus on the top-down view to be able to see the trajectory properly. So here's the marginal agents in action. The marginal agents find it very difficult to coordinate their actions in tight space behind the sofa and end up not completing this in the budget of 250 steps per episode, per agent. The sync agents, on the other hand, can coordinate their actions by moving the object over the sofa. As they get close to the goal, they're actually in a bit of a pickle because one of these agents, even though their actions are coordinated, one of the agents is blocked on the right. So they cannot move as an assembly towards the goal. So they end up using and rightly coordinating the move object actions, which is just move the object and not themselves to complete the task. An obvious question that comes to mind is how many mixtures are enough for sync? In our ablation, we obtained diminishing returns or diminishing improvements for adding mixture components. So one component gave us 33% success, 2 gave us 50, and 13 gave us 59. So it's obviously nice that we can get most of the juice with just a few components. That brings me to the end of the second part of the talk, which is, and the takeaways for this part are that furniture moving is a natural continuation of furniture lifting and needs intricate coordination, which leads to a high rank joint distribution. We found that the reason why previous methods struggle at such coordinated tasks is because of their independent and decentral execution leads to a rank 1 outer product distribution. Then we talked about the mixture of marginals as a neat way of circumventing this rank 1 constraint and implemented it using deep nets as sync policies. I can pause here for some more questions before I move to the short final part of the talk. If there's any clarification on anything which you found interesting, I can do that as well. We have time, at least as per my calculations. Okay, noticing no questions. Maybe I'll pause for a little more if someone's on the verge of asking one. Okay, that completes the two parts of the talk, and brings me to the final sort of still work under submission and on arXiv, and I'll discuss this in brief. This part is called GridToPix. GridToPix is a way to train these visual embodied agents with minimal supervision. And to do this, we leverage perfect perception grid worlds as an intermediate step. That's a lot to take in. Let's dive in and motivate this step by step. So based on my experiments at the intersection of RL and vision, I'll mention three important findings that build the motivation for GridToPix. The first finding is based on something I haven't discussed in previous parts of this presentation. That is the training methodology for these visual agents. How do these agents, how are they trained? What is the reward structure and so on? The visual RL agents that I showed before, or in general, other works have also worked on, need handcrafted or shaped rewards. These shaped rewards serve as dense indicators of success to the agents. So for example, in the furniture lifting task I discussed, the agents are warm started with optimal actions, leading the agents onto the shortest path to the goal. For the furniture moving task, the agents are given a positive reward for moving the furniture item closer to the goal. Even in popular single agent navigational tasks like point goal navigation, a similar positive reward is allotted if the distance to the goal is reduced. And in other collaborative multi-agent tasks that came out after us, like Google Football, dense supervision in the form of checkpoint rewards is shared with the agents. This indicates whether the agents have been able to move the ball closer to the goalpost. I personally found it unsatisfying to have to design and shape the reward structure for every embodied task I was working on. So I went ahead and tested agents on these three tasks without these dense and shaped rewards. That is using terminal rewards. This leads to the second finding. We found that agent success drops to near zero when training with terminal rewards. Often no meaningful policy was learned despite training them for millions of steps. And this isn't true just for the task I discussed or we created. This is true for these drastic drops were seen even in other tasks like point goal navigation and Google Football when I trained them with terminal rewards. So training with terminal reward. So just to clarify this, when I say terminal rewards, I mean that the goal dependent rewards or the success rewards are available only at the end of the episode and not as dense indicators during. And training with terminal rewards is a general way of giving supervision to RL. It's a minimal way of giving supervision to RL agents. Why? Because as tasks become harder, it's impossible to explicitly write rules of giving shaped rewards to the agents. The third finding on RL vision, or more of an observation, is that terminal rewards have been widely used to train general RL agents. Particularly, terminal rewards can teach efficient policies in very complex competitive games such as chess, shogi, Go. Even multi-agent cooperative games like Hanabi have found that terminal rewards are sufficient. Simplistic navigation environments like Minigrid can also learn from terminal rewards. So why can these agents learn policies from terminal rewards, but not our visual embodied agents? The answer is because these agents have perfect perception. So what do I mean by perfect perception? I mean that the semantics needed to solve this task are directly available to the agent in its observation. That is, no perceptual reasoning is needed on top of there's no raw observations to be processed. This could mean providing a tensor with current and previous positions of the board pieces for any of these games. or providing the explicit card information for what the players hold in their hand and their previous moves. And for navigational tasks, it could mean providing positions and states of every relevant object in the scene. For example, telling that this door is red and it is currently locked. And this is a key, which is also red, that can be used to unlock this door. So if you give this perfect perception in the observations, agents can learn policies from the minimal supervision of terminal rewards. Quickly summarizing these findings, we know visual agents need shaped rewards. I tried visual agents with terminal rewards and they don't work. And we know that very complex policies can be learned if the agents have perfect perception. This brings me to the idea of GridToPix. The first step to doing this is to create mirroring grid worlds for these visual environments that we have been talking about. And once you have these mirrored grid world environments, you first learn planning in these grid worlds, and then learn perception in visual worlds. So you decouple the problem of planning and perception into two steps of first learning planning and then learning perception. So we went ahead and created these mirroring grid worlds for existing visual simulators. As a matter of fact, we didn't have to do much work because these grid worlds existed in some form or the other for visualization purposes, but no one was training agents on them. Let aside, no one was using these agents as experts in any way. These grid worlds capture positions and states of the object. It can capture semantics such as where can this furniture item fit, or where have I been before, or where can I go next. Any other semantic can be included in a tensor representation for these grid worlds and provided directly to grid world agents. The obvious question is, how do these grid world agents do? These grid world agents can learn from terminal rewards. We found that if you trained a grid world agent for the same task using terminal rewards, this 1% success becomes 56% success. This 0.1 SPL becomes 78% SPL. And the game score, which was 0.07 with terminal rewards in visual environments, becomes 0.9, which is 90% success in grid world environments. So grid world experts can solve tasks if they are given perfect perception. Next, we move to decoupling planning and perception using this two-stage approach. The idea is quite simple, and it involves this teacher-student sort of collaboration between agents. So in stage one, we train a grid world agent using terminal rewards, and then we train a visual agent by receiving free supervision from this grid world teacher. We can execute actions in tandem in both the grid world and the visual worlds.
Possibly we've lost audio. I'm not sure if you can still hear us or not.
Can someone acknowledge once again?
Yeah, now we can hear you.
Okay, great.
Thanks.
Yeah, let me just recap for myself and for others. Let me just go 2 slides back. I was saying that once we have these grid worlds, which have performed super well for the same tasks using terminal rewards, we can go ahead and do this two-stage decoupled learning of planning and perception. That is, we train a grid world agent using terminal rewards, and in stage one, and then in stage two, we train a visual agent by receiving free supervision from this grid world expert. So we can execute actions in tandem in both the grid world and the visual abstraction of the world, and use imitation learning to distill policies from the grid world teacher to the visual student agent. And at test time, we don't need the grid world expert. We can just execute this visual agent in new environments that it hasn't seen ever before, with no need for access to the grid world expert. So this two-staged decoupled learning of planning and perception, how well does it do? So this is where we were when we tried present visual agents with terminal rewards. And GridToPix can enable learning from terminal rewards with this decoupled planning and perception. So with terminal rewards, you can have 25% success instead of 1% success. You can have 64% success instead of 0.1%. And similarly, a big gain in football environments as well. Finally, even in the shaped reward setting, this decoupled learning of planning and perception can yield better results than training direct visual agents or the DirectPix agents. So that's 58% accuracy in with dense rewards or shaped rewards can be boosted to 62, 55 can be boosted to 69, and so on. Let me quickly summarize the takeaways for all three parts of the talks, particularly the third one at the end. We talked about collaborative behavior in visual environments. We discussed explicit, implicit forms of communication and how they affect performance. We interpreted the communication that emerged between the agents when we just gave them the structure to talk about, but they decided what to talk about. In sync policies, we discussed this intricately, tightly coordinated task of furniture moving, why previous models fail at it because of the rank 1 constraint that they have, and how mixture of marginals and its implementation in deep learning sync policies can help circumvent this problem. And here in GridToPix, we discussed how current visual RL agents crave dense shaped rewards. And GridToPix leverages grid worlds as free supervision and leads to improved results in both the terminal and shaped reward settings. I'll pause here for some questions on the GridToPix side. Can help clarify any concerns. Let me go to this slide for people to remind themselves what GridToPix is.
Maybe a quick question on your last work, the GridToPix. Could you also pose this the other way around in kind of like a discretized or grid-like version of SLAM, as in your agent moving around, building up the map, or do you always have to run this? Or why did you decide to run this in the student teacher version in the first place?
So what is the alternate that you were thinking of?
As in, like the agent starts without any knowledge of the map and basically builds the map while exploring, which would be the traditional SLAM setting. Why did you decide to go for the other way around?
Right, because this geometric projection of the raw observations on a top-down space will give you these observations in a top-down view, but will not give you semantics yet, right? Our objective was to see that can these complex tasks be achieved if perception is abstracted away. And that's why this top-down map doesn't just have raw pixel observations. It has semantics baked in as a tensor. So you know where the goal is, you know where you are, you know what is an obstacle or where the obstacle is, where the boundary of the scene is. So any form of environment state information that your environment has access to, you can first let this grid world teacher have access to it and learn how to do things. And then in the second stage, once it knows how to do things in perfect perception, learn how to do this from raw observations.
Okay, but here basically in the second stage, it establishes the link between its partial observation of the first person view to one grid cell, essentially, right? So where am I in the grid cell?
It does much more than that as well. For example, it learns, for example, these are correspondences, like this is the ecocentric grid world observation, and this is the ecocentric visual observation. So it knows that this is an area that I can navigate through. So this thing is worth navigating through, and all of this area is occupied space, which is not useful. It also knows while training, not during test time, that the goal is right in front of me, so I should be moving forward.
Mm-hmm.
So it's not just a per pixel to grid world correspondence. It's also, the availability of free semantics, and then learning, planning on top of it. I think a good way to incorporate what you are suggesting would be to, and I have thought about it, of presenting this work in this way, that I am a visual agent hallucinating a map in my mind, or, and I could have a loss on top of it. So basically, I could be projecting these things on a top-down map and getting a loss for learning the semantics in this hallucinated form. Very similar to how when we navigate, in our college campus, we know a map of the Google map in our mind that, okay, I need to go 2 streets north and 3 streets on the west. And that's a more theory of mind sort of, or like self-play sort of version of this, this idea. I think that also works, should work in theory. I thought of it in this, decoupled learning setup, that, let's take what is the problem with these visual agents. The vision is the problem with these visual agents. let's abstract vision. I being a vision person, doing grid world teaching, teacher training was against my religion. And then I transferred this grid world agents to these pixel agents.
But it's still it's a very nice way of basically getting rid of partial observability, essentially, because you do the planning in the complete fully observable MDP.
Right. There's still some partial. We still keep some partial observability in terms of limited view of the environment, which can also be given away. But there is another work which I'm working on, which I have an arXiv report on, that if this expert is actually too privileged or it knows too much, transferring policies becomes difficult. And I'll point you to this imitation gap paper on my webpage if you're interested in this area. That
Thank you.
What if you went ahead and removed all partial observability? Would that be good or bad? Like if you take it to the extreme, that's a question which that paper addresses. Yeah, I think just as loose pointers, I wanted to keep this, one slide, summarizing things and suggesting that, these collaborative visual agents are just an intermediate, nice space in between. You could use collaborative learning to better learn visual representations. Think of, not having intrinsic. So for example, there's curiosity-driven learning where curiosity was a way of supervision, self-supervision for learning representations. Collaboration, or the impact that you have on collaboration, could be another way of learning better representations. You could use this, just like the sync policies, to develop better multi-agent RL insights. Or you could take these simulated world agents and put them to real world. And there are some works which kind of in the same spirit as this, that they tried things in simulation of collaborative, robotic arms, and they found that the policies that you learn in that space to translate well to robotic agents. So yeah, I think this is a nice sweet space in between, and you can go down the fundamental routes of better multi-agent RL algorithms, visual representations, or apply them to real robots. Finally, I just wanted to make sure I thank all these awesome mentors that I've been able to trick in advising me throughout my PhD tenure, and a big thanks to them and to all of you for paying so close attention and asking such nice questions. I can take more questions if people have time and they're interested.
Thank you very much for the wonderful talk. Do we have any further questions?
So I have one non-technical question. So what are the applications of multi-agent learning? Well, both in the immediate term and the midterm.
In general, multi-agent learning, or visual spaces. For example, I motivated. I don't know whether I was clear in. So this was a motivation. Like we in all spaces, like whenever we are in the real world, we collaborate and communicate using implicit and explicit cues. And if you're looking for real AI applications, think of self-driving cars. Currently, I've worked at Uber during my internship, and I have friends working in self-driving. They're using LiDAR and various forms of modalities to better learn car driving from a single agent perspective. But these cars do not talk to each other. These cars could talk to each other and prevent accidents, where there is partial observability from the perspective of one car or one agent, but multiple agents together can solve this task. Similarly, think of disaster mitigation problems, where you have sent the swarm of robots on an earthquake site. There's one way that each of these agents or each of these robots can enact independently, or they could communicate with each other and with us to do a better job of moving debris, which is too heavy for one agent to lift, or do a search and divide and conquer sort of a strategy to better search the area. Yeah, these are like I think the idea of collaboration is evident to anyone who's collaborated before, that even on research problems, that you do something which you alone cannot do. And multiple examples come to mind in real world and in robotics. I would love to see Uber, or not Uber now, but Aurora or Waymo, etc., to be able to communicate between cars and relay important information from one to another. I hope that answers the question in some way.
Thank you.
Okay, then since we're a little bit over, we'll perhaps end it there and say thank you very much for the wonderful talk, Unit, and for joining. And thanks everyone. We'll close it up.
It was lovely being here.
Thank you.
Bye.
Bye.